Well, hello everyone. Trig day number 6. Topics for today: solving some trig equations and graphing trig functions as well. Going to use some identities and get some work done. So let's get to it. Okay, let's get started with a review problem from day number 5 material. Given root 2 sine x plus root 2 cosine x equals k cosine x plus b, determine k and determine b. So let's expand that right side. Oops, that should be cosine x. Expanding, I'd get k cosine x cosine b minus k sine x sine b. Alright, outstanding. Let's set equal terms that contain sine x and terms that contain cosine x. So we would have root 2 sine x equal to negative k sine b sine x. Therefore, root 2 should equal negative k sine b, which means that the sine of b should equal negative root 2 over k. Root 2 cosine x should equal k cosine b cosine x. Therefore, root 2 should equal k cosine b. Clearly we can see we're working with angle b in both cases. So cosine b equals root 2 over k. Now you're told here that this is in quadrant 4, but you should be able to tell because in quadrant 4 we've got a positive cosine and a negative sine value. Therefore, we're going to have a triangle that has a cosine of root 2 over k and a sine of negative root 2 over k. This angle being b. Therefore, using Pythagorean theorem or special right triangles, I know that k should equal 2, and of course b would equal negative pi over 4. There you have it. Let's move on to some some solving trig equations using identities and maybe some factoring as well. Okay, let's solve some equations here using identities and factoring methods as mentioned earlier. I see an identity involved here. That'll be 2 sine x cosine x. And I'm going to subtract root 2 cosine x and set the right side equal to 0. Notice here that we'll be working with a restricted range of outcomes. 0 to pi. I'm going to factor out a cosine x. Okay, that leaves me with 2 sine x minus root 2. Okay, zero product property tells me that cosine x must equal 0, or 2 sine x minus root 2 must equal 0. Well, those will yield answers. Cosine x equals 0 means that we're looking for the angle such that the cosine is 0. Well, the only place that that would happen in the restrictions for cosine and in the restrictions here, 0 to pi would be at pi over 2. Okay, and if I were to solve for x in the second equation, I would have that x equals inverse sine of root 2 over 2. Of course, which will yield answers. Sine will be root 2 over 2 in two places in quadrants 1 and 2, which will be pi over 4 and 3 pi over 4. Alrighty, there we go. We got ourselves 3 solutions to that particular equation. Let's look at the second example. Cosine 2x plus 3 cosine x equals 1. This screams, double angle cosine, and it looks like a factoring problem to me, so I'm going to rewrite cosine 2x is cosine squared x minus 1 plus 3 cosine x. And then I'm going to subtract that 1 over from the right side to the left. which leaves me with a factorable quadratic. And I believe I can factor that into 2 cosine x minus 1 and cosine x plus 2. Yeah, I think that'll work. So zero product property, I'll move my work up here, would leave me with 2 cosine x minus 1 equals 0, or cosine x plus 2 equal to 0. All right, which yields a value of x equal inverse cosine of 1/2 and x equal to the inverse cosine of -2. Now, interestingly enough here, this will be no solution due to the fact that a stripped down cosine function, right? So y equals cosine x or y equals sine x that hasn't been stretched at all or shifted vertically cannot exceed 1 or -1, right? So any value outside of that range will not be a possible output from that function. Cosine can equal 1/2 within the restrictions here of 0 to 2 pi, and that'll happen at x equals pi over 3 and 5 pi over 3. Okay, outstanding. Let's move on. It says solve here 2 cosine squared x equal to sine x. Now, I like the idea of, again, using an identity. In this case, I'm gonna write cosine squared x as 1 minus sine squared x. And then I'm going to bring that over to the right side because I'm going to want this negative. I don't like working with a negative leading coefficient when factoring. So I'm going to bring everything over to the right side. So that would be a positive 2 sine squared x plus sine x minus 2. Okay, now we're going to factor that one. That's going to give us 2 sine x minus 1 and a sine x plus 1. I'm going to skip some of the formalities here, and I'm just going to go straight to it. This tells me that x must equal inverse sine of 1/2. And the second expression will yield me x equals inverse sine of -1. All right, so this is going to give me two answers. Inverse sine will give me inverse sine of 1/2. Will give me pi over 6 and 5 pi over 6. You got to know your unit circle, you guys. You just got to know it. And then 3 pi over 2 for here for inverse sine of -1. All right, outstanding. A little bit different flavor here on number 4. It says find all possible values of tan theta given that tan 2 theta equals 3/4. So if tan 2 theta equals 3/4, let's use the identity for tan 2 theta, which is 2 tan theta over 1 minus tan squared theta. Okay, so we're using the identity that tan 2 theta equals what I just wrote. All right. So I'm going to set that equal to 3/4 since I'm given that. I'm going to cross multiply. That gives me 3 minus 3 tan squared theta is equal to 8 tan theta. I'm hoping this is factorable. Bring everything to the right side. We get 3 tan squared theta plus 8 tan theta minus 3, which I believe ends up being factorable. It's 3 tan theta and tan theta. And I get myself, would that be a -1 and a +3. Now, notice the wording of this problem. It asks me for all possible values of tan theta. Well, there's 2 possible values for tan theta. All right, so tan theta could equal 1/3, or tan theta could equal -3. I don't really care what theta is. I'm not looking for a solution for that angle or angles, right? I'm just looking for a ratio for which tan theta equals or is equivalent to. Okay, outstanding. So we've done some solving. Let's get into some graphing. All right, so graphing sine and cosine. So in order to graph sine and cosine, you got to be aware of what these four items are, right? A and B and C and D. In both cases, and actually with sine and cosine, I don't care which one it is, it's going to have the same effect on the function itself. So what A does for a function is, it's first of all, it's called the amplitude, right? If we take the absolute value of A, that gives us the amplitude. Okay. What the amplitude affects is the vertical stretch Okay, it's either a vertical stretch if the absolute value of A is greater than 1. It's a vertical shrink. I'm going to abbreviate here a little bit. If the absolute value of A is less than 1. Okay, and there's a reflection, vertical reflection, if A is less than 0. Okay, so that affects our vertical stretch, shrink, and possible reflection. All right. B. B is related to the period or cycle of the function. Okay, so the expression 2 pi over B gives us the period. Because 2 pi is a typical period length for non-horizontally stretched sine or cosine function, 2 pi over B gives us that new period. So it might stretch out the cycle further, or it might shrink the cycle and make it oscillate quicker. Right? But with B, we get a horizontal stretch. I spelled stretch wrong, that's cool. If the absolute value of A is less than 1. Okay, so there's a horizontal stretch, kind of the opposite of what you think. If I had sine of 1/2 x, that's a horizontal stretch by a factor of 2. If I had sine of 3x, that's a horizontal shrink by a factor of 1/3. So be careful with that. Horizontal shrink, like I said, happens when, oops, look at that. I can't believe that. I put an A there. It should be a B. All right, if B, absolute value of B is greater than 1. Okay, and then of course there's a horizontal reflection if B is less than 0. Okay, let's talk C. Pretty simple. C is called the phase shift. So it's a horizontal shift. Okay, if I have sine of x plus pi, that is a shift left pi units. Okay, so the sign will be the opposite. All right, so if C is greater than 0, then that is a horizontal shift left C units. If C is less than 0, that will be a horizontal shift right C units. Okay, so just so that you're feeling a little bit more comfortable, if I have x minus pi over 2, of course that would be a shift to the right, pi over 2 units. And then D, very nice, easy. This is called our vertical shift. There is no special name for it, although it does form the midline of the function, which we can visualize here in a minute. But vertical shift is if C is greater than 0, we're going up C units. If C is less than 0, we're going down C units. Okay, and the midline of a sine or cosine function, let's take sine here. In this case, if there's no vertical shift, it's the midline. So if C equals 0, then y equals 0 is the midline of that function. Okay, let's get into some graphing here and see all these things kind of take shape. Okay, so let's sketch f of x equals 3 sine of 2 pi, or 2x minus pi. First thing that I always do is I always factor out b, and I'll show you why here in a minute. So this would be 3 sine of 2x plus pi over 2 minus 1. Okay, so it looks like a equals 3, looks like b equals 2, c equals pi over 2, and d equals negative 1. All right, so for me, what that tells me is that if I'm shifting down 1 unit, my midline is going to be at y equals negative 1. Okay, that's my midline. I kind of always do that. I like to set my bounds and kind of the location of the upper and the lower bound. Okay, so if a, our amplitude, is 3, that means midline to max value will be 3 units. So this would be my upper limit of my function at y equals 2. This distance is a, so a equals 3, or the absolute value of a equals 3, right? Therefore, also, we would see that same distance show up here. So our minimum value would be here at y equals negative 4. So our function is going to oscillate within these two parameters. So in this way, I've taken care of, you can kind of check the block on the vertical transformations. Okay, seeing that there's no vertical reflection, but I have stretched my function and I've shifted it down. So now let's locate where the function will be. Okay, so the period is going to change. Okay, so I'm going to graph the original sine function, right? So an original sine function will look like this, right? It would start here at 0. It would max out at pi over 2. It would hit 0 again at pi. Minimum value at 3 pi over 2, and then of course would finish up right here. So this is what sine x, ooh, that was poorly done. Let me try that again. Much better. So that would be y equals sine x. Now I'm going to do these horizontal transformations to our function. So I'm going to take, to find my period, new period, I'm going to take 2 pi over b, and b is 2. So our new period is pi units. So our function is being shrunk horizontally. Okay, so now it's going to oscillate twice as fast. Just like that. Okay, we're also doing a shift. So when we work on the inner transformations, we have to work in the opposite order of operations. So I perform the stretch or shrink, in this case, a shrink, and then I perform the translation. So we're going to shift this, how many units? Pi over 2 to the left. Okay, so let's shift our function pi over 2 units to the left, which would be this. And then the last step that I have to do to finish this off is I have to then perform those vertical transformations, which is stretch it by a factor of 3 and shift it down 1 unit. And that's really easy. All I'm going to do is move my points to the appropriate locations. And I've got my function. So my purple function sketched on the graph is 3 sine of 2x plus pi minus 1. Okay, let's look at another example. It looks to me like I'm going to have a equal negative 1, b equal to a half, and I got to do a little factoring here real quick before I can really see what C is, Charlie, that is. Okay, I'm going to factor out a half, which is going to leave me with 3 pi over 2. Okay, so I have no value for D, so D is 0. So C is negative 3 pi over 2. Okay, so let's see what we've got going on here. Again, I'm going to look at my vertical transformations. Looks like my midline is at 0, because D is 0. So I'm not going to change anything with my midline. Okay, so that's y equals 0. And since a is -1, I'm not going to change anything with regards to the location of my max values and min values. Okay, so almost everything is going on horizontally. Okay, so let's first graph negative cosine x. Y equals negative cosine of x. So cosine of x, it starts like this. Oops. And it has a minimum value at x equals pi. And looks like that. Okay, so there's that's actually positive cosine x. Let's write out negative cosine x, and then we'll do looks like a horizontal stretch and a shift. Okay, so now let's flip it vertically. Alright, so I've got myself negative cosine x. Now I just have to stretch this horizontally, because as we'll see here, 2 pi over b is going to equal 4 pi. And then I also have to shift this, it looks like to the right. Oh boy, that's going to go off our graph. That's okay. 3 pi over 2. Okay, so I'm going to take this graph and really what it's going to look like if I were to y equals negative cosine. Let's do the stretch first. 1/2 x, right? Let's stretch this horizontally. What it'll look like is this. I won't be able to see it all. I'm going to take that blue graph and stretch it horizontally like that. So you can see that the graph will end up looking kind of like this. Right? We stretch it out horizontally, doubling its period or its cycle. All right, so that's kind of where we would be, and then we're going to shift to the right 3 pi over 2. So I'm going to kind of do a little makeshift graph here. Not my best, but we'll deal with it. Okay, and if I shifted that purple graph, let's first of all isolate where this would be. This would be at 4 pi, right? X equals 4 pi. So if I shift that 3 pi over 2, that would end up at 11 pi over 2. Okay, 11 pi over 2. If I shift this point right here, 3 pi over 2 to the right, that would be here. Oops. Yep, here at 3 pi over 2. So from 3 pi over 2 to 11 pi over 2 is a length of 4 pi. Right, so that would be the location of what we would call that first min, that second minimum value. So from valley to valley, if you will. So of course that would be at -1 as well as -1. We would hit zeros. Well, let's go actually to the max value of 1. Would be halfway in between those two. So we would add 4 pi over 2, which is 2 pi, which would put us here at 7 pi over 2. Okay, and then halfway in between those is where we'd hit our zeros, right, which would be 5 pi over 2 and 9 pi over 2. And that would be not perfectly drawn, but based on my markings, that would be an accurate graph, even though it looks like a bunch of hot garbage. Okay, guys, so that's a kind of a rundown on graphing. Again, I would factor out B and then perform the horizontal transformation, or the horizontal stretch or shrink first, and then do the shift left to right. Okay, let's look at tangent. Okay, so tangent, there's not a whole lot different with tangent, and I'm actually only going to highlight one thing. It's going to be B. Okay, so with tangent, the period length is actually just pi units. So pi over B equals the period. All right, everything's the same with amplitude, with horizontal shifts or phase shifts, as well as vertical shifts. Now, with amplitude, it's slightly different, because tangent's graph, as you'll see here, has vertical asymptotes. So it doesn't hit a max value. It just has a the amplitude is more of a stretch, right? So if this were tan x, then 2 tan x would stretch just a little bit faster, right? So it would take off quicker in both directions, right? So it's a vertical stretch, but doesn't have anything to do with a max or a min value. Okay, so let's look at this example for graphing tangent. Okay, so normally what we have here is vertical asymptotes at negative pi over 2 and pi over 2, and then every pi units. All right, so graph of tangent should look like this. And this isn't perfectly to scale. I'm not going over all the details or coordinates that are on these graphs, or on these stems of the graph, but there's an infinite number of vertical asymptotes. Okay, and it repeats itself. Tangent is an odd function. Not odd weird, but like odd origin symmetry. So this is a graph of tan x. So let's graph negative 2 tan x over 3. So what I've got here is a equals negative 2. So that means there's going to be a vertical reflection and a stretch by a factor of 2, as well as b equals a third. Therefore, the period, now instead of being pi units, so here's the period length of the normal pi units, the period is now going to be pi divided by a third, which is 3 pi. Okay, so I'm going to do just a change in labeling, if you will. So this was pi units. Now it's going to be 3 pi units. And there's not been a horizontal shift at all. So that's going to take what was pi over 2 and make it 3 pi over 2. We're tripling the period length. Therefore, instead of going from negative pi over 2 to pi over 2, we're going from negative 3 pi over 2 to 3 pi over 2, which is a period length of 3 pi units. Okay, now we're also going to do a vertical reflection as well as a stretch by a factor of 3. So if you can imagine with me, if I were to just reflect tan x, it would look like this. And one special point that you'd see on there would be the point, well, on the original at least, you would have the point pi over 4 comma 1, because the tangent of pi over 4 is 1. Now you won't see negative pi over 4, 1 over here on the new function because it's been stretched by a factor of 2. So you should see over here, this point, negative pi over 4, oops, I'm sorry, 3 pi over 4, right? Because we did the horizontal stretch, 3 pi over 4, comma 2, right? We've doubled the output. We've doubled the output. Okay, it used to be down here, this was the point, negative pi over 4, negative 1, but now we've stretched it horizontally by 3, so that'll be a negative 3 pi over 4, and then we've multiplied it by negative 2, which would make a negative 1 a positive 2. So this would be one period of the tangent, negative 2 tan x over 3. Okay, and then I'll just place this point down here as well. This will be the point 3 pi over 4, negative 2. All right, awesome. And of course that will repeat itself in an infinite number of portions on that graph. Okay, nothing's changed with the vertical asymptotes because they're totes because there's no horizontal shift going on. Okay, I think I got one more slide here, so let's get to it. Okay, a little bit more with graphing. At times you might be asked to write an equation for a graph. All that you're going to want to do first is identify amplitude. It looks like that goes from 4 to 7, which is a 3. Okay, looks like the period length from max to max or min to min. I'm going to take a little gander here. Looks like it's still 2 pi. So the period 2 pi. looks like if I wanted to call this a cosine function, let's say I trace this portion of the graph, we go with a cosine. We could also go with a sine. It's just typically easier to work with a cosine function because you go max to max and min to min instead of like midline here to midline here. So I typically use cosine, but you may be asked to use a sine function instead. So I would write, it looks like since it starts, my portion of the graph here starts at a max and ends at a max, there would be no vertical reflection at all. So I would call h of x, that would be 3 cosine. Is there a shift going on? Yes, pi units. The period is 2 pi, therefore b would be 1. Since we're shifting to the right pi units, I'm going to subtract pi, and I'm vertically shifting to that midline at 4. Okay, so there you have it. There is h of x as cosine. Let's write h of x as a sine function. Again, nothing will change with the 3. I'm going to go from midline here to midline here. So the portion of the graph I'm going to look at is there, right? So not a whole lot different other than horizontal shift. That would be 3 sine of x. That's to the right pi over 2 units minus pi over 2. And what would that be? Plus, just be plus 4 as well. Outstanding. Okay, let's look at the second example. Very simple. Let's call this t of x. It looks like we could start with a nice sine function here. And we got a max value of 2, min value of 2. And it looks like a period is a length of pi units. Okay, so we can go from midline to midline in pi units. Okay, so that tells me that if the period is pi, and that's 2 pi over b, then b would have to be 2. So b has to be 2. It looks like a also has to be 2. And since our graph is increasing initially, then we know a is positive. C, I'm going to just say is 0, no shift. And vertically also d would be 0 as well. So t of x in terms of sine would be 2 sine of 2x. Too easy. Funny. All right, now cosine, if we went from max to max, all right, t of x, again, would be a positive 2 cosine of 2. What would be the horizontal shift here? Looks like pi over 4 units. X minus pi over 4 units. Cool. When you go from sine to cosine, there will be no change in b. There will be no change potentially in a unless you choose to make it complicated, as well as d. So the only change will be with c potentially, unless you decide to make it more tough on yourself. All right, the amount of sunlight in Iceland on the shortest day of the year, June 21st, is 5.82 hours. Okay, so let's say A of 621, so the amount of sunlight on 621 is 5.82 hours. And the amount of sunlight on 1221 is 18.92 hours. Okay, so I know I have a min value of sunlight. This can't be right. Yeah, let's flip-flop these. There's no way the shortest day is in June. Or is that because it's in the northern hemisphere? I don't know. I don't even care. I'm going to flip-flop those two. So I'm going to put 18.92 as the longest day and 5.82 as the shortest day. Okay, so let's just sketch this out. All right. There's never 0 hours of sunlight, so we don't have to worry about it touching the horizontal axis. So we'll call this t is in years. T in, not in years, what the heck, in days. Okay, and then A in hours. Okay, so we have a min value on 621. And that min value is, oh my gosh, a max value on 621. And that max value is 18.92. And we have a min value on 1221. And that's at 5.82. Okay, so I got a min value here in December for sunlight and the max value in June. We're going to take the assumption that it's trigonometric. So then the next year, June 21st, we should get our next max for sunlight. So the period, oops, let me do that in a different color. Our period length should be 365 days. So let's talk B for a second. B should equal 2 pi over 365. Okay, what is A going to equal? Well, A will be our max value minus our min value, and we're going to divide it by 2 because we want to find the value in between them. So we're going to take 18.92 minus 5.82 and get a value for, which for me on the calculator comes out to be 6.55. Okay, so our amplitude is 6.55. C, if I'm using cosine, C will equal, I don't know, let's call June 21st. What day of the year would June 21st be? Oh my gosh, okay. July or January 31. Let's assume February has 28 days. 31. April has 30. May has 31. June has 30. So let's back that up to the 21st. Let's add those up, and that'll give us the day number. So 3 times 31 plus 28 plus 30 plus 21. We're getting to know each other, you guys. That's number 172. 172. Okay, so C is 172. And actually it's negative 172 because we want to shift to the right. And D will be our max value plus our min value divided by 2. Or what you could do is take your min value and add A. All right, I'm going to do min value plus A, which should be 5.82 plus 6.55. Okay, so I'm getting a D value equal to 12.37. Okay, so let's write an equation in the form for cosine. Y equals A cosine BX plus C plus D. So Y equals A, which will be 6.55, cosine B, which is 2 pi over 365. Oops, I'm sorry. If I want the period to equal 365, I might have goofed that up. Let's see, 365 equals 2 pi divided by B. No, that's right. I'm good. Gosh, I questioned myself there for a second, and I was okay. Minus 172, because our first max is at June 21st, and then plus 12.37. There you have it, guys. That is an equation representing the, or trig equation representing the sunlight in hours in Iceland, where apparently they're all jacked Vikings that just lift logs over their head and throw stones. So, long notes today, but dig into them. Let me know if you got questions. We'll see you in the last video, day number 7 for trig. Have a great day.